So this video is to revise calorimetry in thermochemistry chapters. So I'm going to highlight a few important things in calorimetry subtopic. In this subtopic, there are two learning outcomes. The first one is to calculate the heat change in a constant pressure calorimeter, simple calorimeter, and the second one is to calculate the heat change in constant volume calorimeter, bomb calorimeter. So usually there are two types of calorimeter. The first one is called bomb calorimeter or constant volume calorimeter, which is used to measure the heat of combustions. So the second calorimeter is simple calorimeter, or also being called as constant pressure calorimeter, which is usually used to measure heat of neutralizations and heat of solution. Calorimetry uses the principles of conservation of energy. The reactions, such as combustions and neutralizations, usually release heat, and the heat released is absorbed by the surrounding, which can either be the calorimeter, water, or solutions in simple calorimeter. We shall look at bomb calorimeter first. Bomb calorimeter is usually used to measure heat of combustions or enthalpy of combustions. There are usually three different situations to calculate the heat of reactions, which mainly differ in terms of surrounding. For case 1, the surrounding is calorimeter and water. Hence, the heat released by combustion's reaction is absorbed by both calorimeter and water. How do we know that which situations based on the question? For case 1, information for water and calorimeter is always been given in the questions. Water usually is given in terms of mass and calorimeter in terms of heat capacity. So we shall look at the examples questions. From the questions, we can see that naphthalene is the substance that is being combusted and release heat. And the surrounding here is water and also calorimeter, since the mass of water and also the heat capacity of calorimeters are being given. To solve this question, first, we shall look at the definitions of enthalpy of combustions. It is defined as the heat released when 1 mole of a substance is completely combusted in oxygen under static condition. And the substance that is combusted here is naphthalene. So, means that step 1, we shall first calculate the number of moles of naphthalene combusted first. Then, in step 2, we calculate the Q reaction, which is corresponding to the heat release when 0.01121 mole of naphthalene is combusted. As discussed before, the surrounding now is water and calorimeter, so both terms must be included in the calculations. So in step number 3, only we calculate the enthalpy of combustions by equating 0.0121 mole of naphthalene calculated in step 1 with Q reactions determined in the step 2. Then we calculate the amount of heat released when 1 mole of naphthalene is combusted, and it is equivalent to the heat of combustions of naphthalene. For case number 2, the surrounding is calorimeter only. This is because water and calorimeter are being integrated as one part of the system. Hence, heat released by the combustion's reaction is deemed to be absorbed by the calorimeter only. How do we know? Based on the question, it is case number 2. So we can see that in the question, the information is only given for the calorimeter in terms of heat capacity. So now we shall look at the examples question. So in these questions, we can see that the substance combusted is sucrose, and the surrounding is just the calorimeter, as only the heat capacity of the calorimeter is being given. To determine the enthalpy of combustions of sucrose, again, the 3 steps as in case 1 is being followed through. So step number 1 is the same. We calculate the number of moles of the substance combusted, and for this question is the number of moles of sucrose. Then in step number 2, we calculate the Q reactions corresponding to the 0.002953 moles of sucrose combusted. And for case number 2, as the surrounding now is just the calorimeter, we can see that only the calorimeter term is appearing in the equations to calculate Q reaction. Then step number 3, calculate the enthalpy of combustions of sucrose. First, we equate the 0.002953 moles of sucrose determined in step 1 with the Q reactions determined in step 2. Then we calculate the heat release for 1 mole of sucrose combusted, and it is same with the enthalpy of combustion of sucrose. For case number 3, usually it is the applications of enthalpy of combustion whereby the surrounding is said to be water only. Hence, the heat released by the combustion reaction is deemed to be absorbed by water only. So how do we know that from the question? It is case number 3. So for case number 3, usually only the information on the water is being given in the question. Or in the question somewhere stated the assumptions that all the heat released by the reaction is used to heat up the water. We shall look at the examples questions. So in these questions, we can see that ethanol is the substance that is being combusted and release heat. And the surrounding is only the water, as the information in terms of mass of the water is being given, and in the questions also stated that the heat released by the reaction was used to heat an amount of water. So how to solve this question? So similar to case number 1 and 2, follow through the 3 steps. Okay, so in this question, ethanol is the substance that is being combusted. So step number 1, we calculate the number of moles of ethanol first. Then we calculate the Q reaction. So in case number 3, the surrounding is just water as assumed in the question. That's why in the Q reactions equation, only the water term is appear in the equation. Then step number 3, to calculate the enthalpy change of combustion of ethanol, first we equate 0.03261 moles of ethanol we calculated in step number 1 to the Q reactions that we determine in step number 2. Then we calculate what is the amount of heat released when 1 mole of ethanol is being combusted, and that amount of heat is equivalent to the enthalpy of combustion of ethanol. To calculate the heat of combustion or enthalpy of combustion, we just need to follow through the 3 steps. However, the 3 steps might not always be in sequence. The sequence can be varied according to the questions. For example, in this question, in these questions, we can see that 10 grams of propane is the substance that is combusted and release heat. Okay, and it is case number 3, whereby only information of the water, the mass of water is being given. There is no information on the calorimeter which is being given. So this is case number 3. However, to solve this question, we cannot follow through the 3 steps in sequence. We need to see, first we can still calculate the number of moles of substance combusted, and here is the propane. But for step number 2, to calculate the Q reaction, we can't do that first because we know that this is case number 3, so the Q reactions will be negative MC delta T. Delta T is change in temperature, but in this question, there's no information on temperature that allow you to calculate the change in temperatures. Hence, we can't calculate the step number 2 Q reactions first. But there is another information that is being given to you, that is standard enthalpy of combustion, your delta H combustions. Okay, so we know that the delta H combustion, it is for 1 mole of propane. Okay, so means that before we do step number 2, we shall do the step number 3 first. From the step number 3, we can calculate the Q reactions, which allows us to put into the step number 2 to calculate the change in temperature. We shall look at the solutions in next slide. Okay, so how to solve this question? So first, we can still do the step number 1 to calculate the number of moles of propane, but we can't do step number 2. Remember, there's no information on temperature that is being given to you, so you cannot calculate Q reactions. But we can do step number 3 first because there is information on the standard enthalpy of combustion that is being given to you, and that information is for 1 mole of propane. Okay, and then we can do the ratio to calculate what is the Q reaction when 0.2273 moles of propane is being combusted. Remember from the questions, we already deduced that it is case number 3. That's why the Q reactions term is only having the water term in the equations. Okay, so the Q reactions is obtained from the previous step, then can just substitute it into the equations to calculate the change in temperature.